Hello and welcome to another video lesson with Takoa Lawson. Today we're going to be looking at some example problems for the circular motion unit. First, we're going to imagine an object that's shown here, a mass sitting on top of a table, and the table is rotating. Sometimes they call that a turntable, like a record player. But essentially, it's a plate or a flat disk that's rotating, and a mass is sitting on top of it. This will be different than some other forms, like we might imagine that mass being attached by a string, then be a force of tension. But since this mass is sitting on the surface, it's not a force of tension acting on it. The distance from the axis of rotation is shown here as the radius of rotation, or r, and that we can see that it's rotating in this direction, or if I was looking down from above it, then I would see it going counterclockwise direction. We are given some specific information about it. We know that the distance between the mass and the axis of rotation is 0.3 meters, and we know that it completes 45 revolutions or 45 rotations in 2.5 minutes. This can't be a frictionless surface, because if the disk didn't have friction between it and the block, then the disk would simply spin underneath it and the block wouldn't move at all. The block's inertia is making it want to remain at rest. But since there's friction between that, that means that it ends up moving with it, and sometimes students think there would be a tangential friction. There's not a tangential friction because we're not speeding up or slowing down. We're rotating at a constant 45 revolutions for every 2.5 minutes, so there is a force of friction, but it's not tangent. The best way to start this problem is to start with a free body diagram. If we were looking at the free body diagram for this block, there's the obvious that if there's friction, there has to be a force of gravity, because you can't have friction without gravity pulling you down. And then if you're sitting on a flat surface, even if it's moving, that means that that flat surface is pushing up, or there's a normal force. And since we're not accelerating up or down, some of the force in the y direction is going to be 0. That gives us some information about the relationship between the force of gravity and the normal force. Of course, we know we can calculate the force of gravity by taking mg. And sometimes students think those are the only forces present, because if a block's sitting at rest on a table, then it would be. However, we're going in a circle, and one of the fundamental principles, or one of the concepts that we discussed in the last lesson, is that in order to go in a circle, you have to have a force towards the center of the circle. You have to have an acceleration towards the center of the circle. By definition, you can't go in a circle without such a force. Given this point for the block, there has to be some force to the right. It's required. Now, if I didn't know what it was, I would just call it an FC, some centripetal force, some force towards the center that I don't know what it is. Since it's a block on a friction surface, and since the block wants to keep going straight, its inertia wants to keep going straight. In fact, if friction suddenly turned off, it would fly straight off of the table at that point in a straight line. It would go straight down or straight across. Instead, it keeps turning. So that means there must be a force towards the center, and that force is the force of friction. So if we're looking at the mass on the plate, those two surfaces that are in contact are not slipping. That means this is a force of static friction. And force of static friction has to be less than or equal to the coefficient of static friction times the normal force. When we look at that free body diagram, we start seeing some of the relationships that should stand out a little bit. A, since the force of gravity down is equal to the normal force in this situation is equal to mg. And since the normal force is equal to mg, the force of static friction has to be less than or equal to mu times mg. So there's some maximum force that you can get out of the coefficient of friction. What we're actually asked is, what is that minimum coefficient of friction that would be possible, right? So you could have a maximum, you could have more than the minimum. If you had extra coefficient of friction, it just wouldn't be at the maximum force. What we're really saying is, what's the minimum coefficient of friction we can have so that the maximum force of static friction is just enough to keep this mass rotating on this disk as shown. Based on the free body diagram, we know that the force of static friction is less than or equal to mu of static friction times mg. We also know that the force of static friction is the net force acting on the object. And when you're going around a circle, that net force is your centripetal force. The net force has to be a force towards the center. In this case, there's only one force towards the center. So it's not the sum of multiple forces. In some cases, we might have multiple forces and have to find out what the net force is. But since there's only a single horizontal force looking at the free body diagram, which is the force of friction, that F net, or F centripetal, is actually the force of static friction. From that, I can take into account that that centripetal force, that center-seeking force, has to be equal to the mass times the speed squared divided by the radius. That's from the fact that it has to be the mass times the centripetal acceleration, and the centripetal acceleration has to be v squared over r. The force of static friction is equal to, or less than or equal to, mu s mg, and is equal to mv squared over r. So what that really means is that mv squared over r is less than or equal to mu s mg. These are the same m's, so we see m ends up canceling out, and this is what I'm trying to figure out. What is that minimum coefficient of friction? So you simply divide both sides by g, or multiply by 1 over g, and we find out that the answer to this question is that mu s must be greater than or equal to v squared over gr. Now, some students would think that they're done at that point. However, you're not quite. You could take the revolutions per minute and convert them to a speed and then have that as your v squared over r. But if you just put in 45 revolutions over 2.5 minutes, that's not going to be your speed. So one of the questions, some of the ways that they've added a little bit of challenge to this question is by giving us some different units. What I'm really trying to figure out is, what is the velocity? Well, the velocity is equal to the circumference divided by the period. I don't have the circumference directly. I see that I have the radius, so what I really need to do is find a way of being able to write that in terms of the velocity. Now, if I have 45 revolutions in 2.5 minutes, I'm going to have an issue with that unit. The revolutions is okay, because one revolution would be going one circumference. However, the minutes is going to be a problem. So we're going to want to get this from minutes to seconds, knowing that 1 minute is 60 seconds, or 150 seconds. So now what I can see is I do 45 revolutions in 150 seconds. The period is the time it'll take to do one revolution. And right now what I know is 45 revolutions is 150 seconds. I want to get revolutions to 1. You can get any number to 1 by dividing by itself. So I'm going to divide by 45, but if you do something to one side of the equality or the ratio, you have to do it to the other. So what I find out is that 1 revolution is equal to 150 divided by 45, 3 1/3, or to sig figs, 3.3 seconds. Now I know the time for 1 revolution, also known as the period. That's not quite the speed of the velocity, but it's getting me close. Was 2 pi r divided by the period. But I can substitute in for v 2 pi r over t. So I can substitute in for v 2 pi r over t. So this is equal to 2 pi r, the circumference, divided by the period squared, that's v squared, over g times r. We can work some of these out, and we get that the coefficient of static friction has to be greater than or equal to 2 squared, which is 4, pi squared, which is pi squared, r squared divided by r, which is r, divided by t squared divided by g, or divided by t squared times g. Hopefully you can see mathematically why that ends up being the correct values. If you don't, you can just put this over 1, dividing by a fraction, same as multiplying by the reciprocal, and hopefully you'll be able to see it there. Now I have that minimum coefficient of friction in terms of the things that are known here. We know the period, not directly, but we're given the information about it. We know the radius, and of course we know g, that's the acceleration due to gravity. It's going to be 4 pi squared times r, which was 0.3 meters, divided by the period, which we figured out was 3.3 seconds, squared, times g, which is 9.81, although a lot of times students will use 10. Mu s has to be greater than or equal to 0.11086, blah, 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 put to 2 sig figs, 0.11, and coefficients of friction are one of the only numbers that you cannot write units with. Technically, you could write newtons over newtons if you really felt like it, but that would be bad form because coefficients of friction are one of the few numbers that are actually unitless in physics. Let's look at a little twist on the same problem. In this case, we have all the same information, but we're told the mass, and now we're asked to find the force of friction. It actually turns out, if you notice in the last one, the mass canceled out, so it was irrelevant to the question about the coefficient of friction. However, if I want to know the actual force that's present, I have to have the mass to be able to determine that, because a bigger mass would require a bigger force. When we look at the problem, not going over everything again, we really know that the net force, or the centripetal force, was equal to that force of friction. So what they're really saying is, what's the net force acting on the object? What's the centripetal force acting on the object? And we saw that on the last problem when we were working through it. That's simply going to be mv squared over r. I actually don't have v. We could go back and I could calculate it, but we saw in the last one, v squared over r actually ended up being 4 pi squared r over t squared. So I can actually reuse that same relationship. The mass times 2 times pi times r divided by t, because that's the period, all divided by r. Again, we see that we can factor out that r, and we end up getting m times 2 squared, 4 times pi squared times r squared divided by r times r divided by t squared. The sum of all the forces. But since the only horizontal force, or the only force towards the center of the circle, is the force of friction, the sum of all the forces is the force of friction. And that means that we can calculate it out, or that the force of friction is equal to the mass, which was told to us. Of course, grams is going to be an issue. We have to make sure that's in kilograms. So 0.380 kilograms times 4 times pi squared times r, which was 0.3 meters, divided by t squared, which we already saw was 3.3 seconds. Force of friction. The force of friction is going to be 0.4132 blah blah blah, but going to 2 sig figs, 0.41 newtons. Now some students would recognize there's actually a different way of getting the same answer, that the force of friction has to be less than or equal to mu Fn, or in this case mu mg. However, it's less than or equal to that, right? But we have purposely, normally if I just had it was given a mu, I don't know that the force of friction is equal to that. It might be less than that value. For instance, the maximum friction value could be 20 newtons, but as you see here, I don't need 20 newtons to go in the circle, so I wouldn't be at the maximum friction value, so I'd have to use this method. However, based on the last part of this problem, we figured out what's the minimum mu that would allow this to operate as. The minimum mu, then that means we're at the maximum force of friction. The minimum mu means we've reached the limit. If it was any smaller of a mu, we wouldn't be able to do that. In this case, when we know we've got the minimum mu possible, we can actually calculate the force of friction by taking the mu we calculated in the last problem, which was 0.11, multiplying that by the mass, which we're told is 0.380 kilograms, and multiplying that by 9.81 meters per second squared. And if we use this solution, we still get 0.41 newtons. And again, I warn you, it is possible for these to not agree. It's only when we determine the minimum coefficient of friction that either of these methods will work. If we were given the coefficient of friction, unless I knew I was at the maximum speed possible, I would not use this to find the force of friction. I'd use the fact that the force of friction is the only force going towards the center, which means that it's equal to the centripetal force, or the net force acting on the object.